All right. What else do I have for you? Finding inverses of bigger matrices is not so easy. And this is something that we spend time on in linear algebra. There are processes, there are methods to do it, but there isn't a nice formula. There's not a nice formula that you can have like this one to find the inverse of a 3x3 or a 4x4 matrix. You can totally do it. There's just no nice formula. So, okay, just a couple other things here. Matrix valued functions. Matrix valued functions. So if the entries in A are functions instead of numbers, or instead of scalars maybe, then usually what we do, we just change our notation slightly. We write A of t. Instead of A, we usually say A of t in order to denote that we have a function. And so if I want to write this in the shorthand, usually we'll say C sub ij, well, actually this is A sub, that's a terrible A sub ij of t. So we usually say little a sub ij of t. So we've got a whole bunch of functions inside the matrix. Instead of scalars, we've just got functions inside of there. And we can do the derivative of a matrix with functions. This is just the derivative of all of the little individual functions inside. So you just take the derivative, it's called component-wise. Take the derivative component-wise like you would normally. You just take the derivative of all the functions inside of there. Maybe we'll do a really fast example. Let's say that A of t is, I don't know, sine of t, cosine t, e to the 2t, and 4, if I'm reading across. A of t is sine of t, cosine t, e to the 2t, and 4. I can have a number in there. That's a constant function. That's totally fine. No problem whatsoever. So then a prime of t, you can do this just as fast as I can. Cosine of t, negative sine of t, 2e to the 2t, and 0. If you can take derivatives, you can take derivatives of a matrix. Easy, no problem, no big deal. Okay. One last thing for today, and then we are going to finish early. Yet more properties of matrices. So this is properties of matrix derivatives. Properties of matrix derivatives. Virtually everything on here is exactly what you would expect, but we are mathematicians and therefore we don't assume things and we write them down. So that is what we are doing here. First of all, if you want to take the derivative of A of t plus or minus B of t, remember that d over dt out in front means take a derivative. So d over dt out in front. If you are adding or subtracting two matrices and want to take a derivative, I am sad I cannot ask you to give me this in class, but same idea. A prime of t plus or minus B prime of t. Easy, no problem, no big deal, all good. That's exactly what you would expect. If you want to take the derivative of A of t times B of t, if these were functions, we would use product rule. Yes, if these were functions, we would use product rule. We have product rule for matrices. So A prime of t, B of t, plus A of t, B prime of t. Product rule works exactly the same way that you would expect it to for matrices. Totally and completely the same way. One small catch. You have to be careful not to switch the order of matrix multiplication in the first part and matrix multiplication in the second part, because matrix multiplication does not necessarily commute. You can switch the first and second pieces because that's matrix addition and that commutes. That's fine, but you can't switch the multiplication. So you got to make sure not to do that. All right, if I want to take the derivative of a scalar k times a matrix A of t, this is exactly like what you would expect with the constant multiple rule. This is going to be k times a prime of t. Easy, exactly what you would expect, no problem there, all good. And last, if I want to do the derivative of, I'm going to go with capital K times A of t. So capital A is going to be a matrix of numbers. Okay. I could use rule number 2, or I could also say, oh yeah, this is exactly what I would expect. Capital K times A prime of t. This is a special case of rule number 2, right? Because the derivative of a matrix of numbers is just going to be the 0 matrix, right? The derivative of a matrix of numbers is just going to be the 0 matrix. Everything is going to have a derivative of 0. And so one of these two pieces up here is going to go away. So this is just a special case of product rule. Okay, anything for questions at this point in time? That is a lot of matrix properties thrown at you really fast. Like I said, if you are interested, take linear algebra. If you're not interested in your math major, you still have to, sorry. But it's fun, I like it, it's a good class, and you get to prove a lot of the stuff that I just wrote down, which is good and beneficial. I won't ask the people who have taken linear algebra if they liked it or not. I won't put them on the spot. Anything? Okay, I'm getting some nods. All right. Anything for questions at this point in time? Anything that all of that raised? Daniel, yes.
This is kind of random, but do you know if like the transpose of a matrix is equal to that matrix? Does that make it like commutative when it's multiplied?
Yes, because if you're multiplying two matrices together that are equal, you can totally switch the order and they'll be commutative. I think that it is not an if and only if though. If you have two matrices that are commutative when you multiply, they may not have the property that their transposes are equal. Yeah.
Okay, thanks.
Yep. Other questions, other things, other questions. I just threw probably a week of linear algebra at you with no proofs, but probably a week of linear algebra. So, although I don't think we do functions and derivatives in linear algebra, I don't think we do matrix valued functions with derivatives in there. Going once, going twice. Anything else? Okay, that is a good spot to stop. So then Monday, what we're going to do is say, oh yeah, we're taking a differential equations class, aren't we? So let's go and apply what we just learned to differential equations and see how we can do this with, they're called higher order systems. So more than two dependent variables. How can we use this to make that a little bit more precise? We're spending 3 days on section 5.3, so it will be both Monday and Tuesday next week. It's going to be both. I want to spread this out a little bit and not rush through. I know that I could go faster for those of you guys who have had linear algebra before, but since it's not a prereq, I want to make sure to go a little bit slower and give people who haven't taken linear before less of a whirlwind tour. So, okay, thank you. See you on Monday. Have a lovely weekend with nothing going on. And I'll send out homework in just a couple minutes. Thanks, guys. Bye.